So today we're going to be using inverse matrices on systems. We've seen all the bits and pieces up to this point. We've seen what a determinant is. We've seen what the inverse matrix is. We've created it. We've seen what the identity matrix is and how certain matrices, when we multiply them together, create an identity matrix. We know that the identity matrix, when multiplied by any other matrix, assumes to be that other matrix. So now that we know all the bits and pieces, let's put it all together. We're going to be working with 2x2 systems, meaning two equations with two variables. This process works on larger systems. However, the math gets a little tedious and it gets to the point where it's going to take up large areas of space to work a single problem. And realistically, at that point, we're going to be moving over to a computer-based system to solve those types of problems. Right now, what we're working with, the reason why we're working with 2x2 is so that the math is displayed nice and neatly and we don't get caught up in the nuances of how to do the thing in order to understand what's going on. That way we take these concepts and apply them to those larger systems. That being said, you probably know several ways to work systems like this already. Substitution, regular elimination, graphing, that may be about the same amount of time and work, if not maybe a little faster. But again, the point of this lesson is to identify how to use an inverse system or an inverse matrix on a system to get an answer immediately. So without further ado, let's take a quick look at what's going on. So in the guided example, what we've got going on here is it walks us through. If we have a system of equations, x, y equals a number, the first thing we want to do is make sure that the variables are all lined up. I want x and then y on the left side of the equation, and I want my numbers on the right side of the equation. So that's going to help us create our first matrix. Now the matrix themselves are going to be used or created by taking the coefficients of the numbers. So right here I will have a 3 and a 1, and this is part of, let's call this my x column. X, right there. And then I have a 1 and a 4, created as part of my y column. And then the new thing that we're going to put in here is we're actually going to put in our variables. So right now I have x and y. X was my first, y was my second. That way, if I want to attempt to find the dot product, I will take the first row, so 3 times x plus 1 times y. I'll get my original equation. And I'm going to set this equal to 8 and 21. So now that I've set up the matrix, all we need to do now is to identify and create an inverse matrix, multiply both matrices by that, which will in essence cancel out the matrix over here, and I'll be left with an xy equals some number over here. So I want to get rid of this. If this were an equation, it wouldn't be a big deal. Let's say this was a 2x, I would divide both sides by 2. But what we found is that matrix multiplication only works one way, through multiplication. We can't reverse that process with division. We have to create a very special matrix called the inverse matrix in order to kind of fake our way through division. So let's go ahead and set that up. We know that the inverse matrix is 1 over the determinant. We swap and change the signs. So let's go ahead and figure out what is the determinant. So I know the determinant is going to be 1 over AD minus BC. So 4 by 3 minus 1 by 1. This is going to be 12 minus 1, or 11. My determinant is 11. So we know that our inverse matrix is going to be 1 over 11. We're going to swap our 3 and our 4 for 3, and then change the signs on the two 1s. So -1, -1. We're going to multiply this side and this side by this value right here. So just to see what's going on the left-hand side, I'm going to multiply this matrix times that right there. Let's set this up. Let's create our original matrix right here in blue. So 3, 1, 1, 4. Okay? Actually, I think the example right here is we create the 1 over, we flip, we change the signs, and then we actually push that in. We've seen in previous videos that I don't need to push that 1 over 11 in so quickly. In fact, let's go ahead and let's just let's keep it through in the way that this is doing it. I found my determinant, 1 over 11. I'm actually going to push this in and create a true inverse matrix. So that's going to be a 4 elevenths, a negative 1 elevenths, negative 1 elevenths, and 3 elevenths. Yeah, there we go. Awesome. And that just keeps more in line with what's going on here. Now, the next step is we're actually going to do what we're going to do right here. I'm going to take both matrices on each side and multiply it from the left my inverse matrix. So let's copy down our original problem. We have 3, 1, 1, 4. We have an x and a y. I'm going to leave some space and write down an 8 and a 21. Now, the second thing that we need to point out is that order matters. So if I'm multiplying my left set of matrices from the left by the inverse, I also want to multiply from the left on my right side of the equation. So my 4 elevenths, negative 1 elevenths, negative 1 elevenths, and 3 elevenths, I'm multiplying from the left-hand side, going in. I'm going to do the same thing over here. 4 elevenths, negative 1 elevenths, negative 1 elevenths, and 3 elevenths. So the inverse is going in from the left-hand side on both of those examples. Now, the big thing that we know is going to happen is I know that the inverse times this matrix is going to create the identity matrix, 1, 0, 0, 1, which when multiplied by any other compatible matrix basically cancels out. So I know that this is going to completely, do this light enough so we can still see it, but we know that's going to disappear over here, and I will be left with simply our xy equals. And so my xy matrix is the only thing left here on the left. I need to figure out what the dot product of this is going to be. And now, the reason why I didn't want to push that 11th in there is because now I have to deal with 11ths as fractions with this matrix as opposed to dealing with a 4 and an 8 and then dividing by 11 later on. So let's go ahead and crank this out as quickly as possible. So for my first row and column, I'll have a 4 elevenths times 8, which gives me 32 elevenths plus negative 1 11th times 21. So that is going to be plus a minus 21 elevenths. Row, column, done. I'm going to go down to the second row and column. So negative 1 times 8 is negative 8 elevenths. 3 times 21 is going to give me a 63 elevenths. Awesome. So what this does is after I combine these, I have my xy matrix. 32 minus 21 is going to give me 11 elevenths, which is going to be 1. Let's see. Negative 8 plus 63 is going to give us 55 elevenths, which is going to be 5. So the information we're going to take from this is that my answer is x equals 1 and y equals 5. Awesome. So that's the full effect of what we've done. And it makes a little more sense now because we've seen all these little bits and pieces going on. Now we've applied it. So let's take a look at some of the first examples here on the front. Now, on the front, what we're doing is the most important part of this process is the setup. We know a lot of very good tips and tricks, and a lot of students know how to approach this, and they know how to do the math, but the initial setup is a little off. So what we want to take the front is we want to take a step backwards and say, let's just convert these systems into 3 matrices, including the xy matrix, so including our variable set. So for the first one, again, all we're doing is we're making sure everything's lined up. I have x's, then y's, and then my constants. So that means I'm going to take my coefficients of 1 and negative 1, negative 3 and negative 1, set them up with a corresponding x and then y, which tells me that in my matrix, my x was my first variable, my y was my second, equals negative 18, negative 6. Awesome. Nothing more to it. If I look at number 3, I'm going to do the same thing. I'm going to take the coefficients, 6 and 3, which are my x's. My following ones are 5 and 1. And then I list my x, y, my variable matrix, which tells me that x was my first variable and y was my second. Set that equal to a negative 15 and a negative 21. Awesome. So we can see these aren't very difficult. The questions and the confusion comes in when we look at matrices like this. Now, two things happen. I notice that my x's are lined up. I have a y up top, but I do not have a y on the bottom, which is going to tell us one thing. The top matrix is going to be a negative 9, negative 10. We know it's still x and then y. I still know it's 94 and negative 60. But I'm missing my y aspect. So what do I put in here when there's no y value? And now that we've set it up like this, the answer might be a little more obvious. Well, there's no y, so I'm going to plug in a 0. The other thing that we want to point out is that we can do the work on this just as easy as we want. The thing that you might notice is that second equation, 10x equals negative 60. That can be simplified very easily. What you're also allowed to do is you're also allowed to take this equation right here and divide this as you plug it in. So let's divide this whole equation by 10, and instead of creating this system, let's create this system. So negative 9, negative 10, xy, 94. And I'm going to divide each of these values by 10. So that 10x just becomes a 1, that's still a 0, and that's now a negative 6. Now the math works exactly the same in this one as it would in the original, but these numbers when finding the inverse is going to be a lot easier to work with. So if you ever spot that, just go ahead and reduce it before you even start your work. Which leads us to number 7. Number 7, and I want you to create our 3 matrices to set up the problem and include any reductions that might make your life a little easier. Pause the video and pause it when you're done and see how you did. Okay, so now that you've had a moment, let's take a look. So with this one, I'm looking at, I have an x and a y, and here I just have a y. So a couple things are going on. I know it's a 2 by 2, so I'm going to create a matrix with a 2 by 2. I am going to list my variables. Now in this case, I could list them as yx and list this term first, but because my second equation is already set up like this, I'm going to list them in order of x, y. I know the top equation and the bottom equation are both going to produce a value. Now, the bottom one's easy. I have my x, my y, and my constant. The top one, I can kind of skip a step right here and say, hey, 8 and 80, I can divide both of these by 8 and make my life a lot easier. That negative 8y becomes a negative 1. That 80 becomes a 10. The thing that I'm missing is I'm missing my x term, which we know when we're missing a term, I'm just going to plug in a 0 value in that matrix. And there we go. So again, creating the system isn't too bad, which that's going to bring us to actually solving the system. So on the back side here, what we're going to do is we're going to actually solve this system using an inverse matrix. So let's go ahead and set this up. Number 9 is going to give us a 1, 1, 3, 2, x, y equals negative 22, negative 18. Awesome. So my first step for the system is I need to find the inverse matrix. So let's go ahead and do that. This is going to be 2 steps. For my determinant, I need to figure this one out. Let's see, that is going to be AD minus BC. So that's going to be 1 times 2 minus 1 times 3. 2 minus 3 is negative 1. My inverse matrix, when I do that swap and change thing, I'm going to swap that 2 and 1, and then I'm going to make that a negative 3 and a negative 1 for the other diagonal. I'm going to plug in that determinant, so 1 over my negative 1, because that's going to go on the bottom right there. And this is my inverse matrix, that scale value and that matrix. Now with this, I have that's not a hard fraction to push in there. Normally I would wait until the end. I'm gonna go ahead and when I write down my next step, I'm gonna push that -1 into every one of those terms. So instead of being 2 negative, negative positive, it's gonna be a -2, +3, +1, -1. Go ahead and write out the last bit of this. Now I'm also going to include that same matrix over here. Remember, we're doing it in the same order. So if I'm doing it from the left over here, I'm doing it from the left over here. Awesome. So I've got that set up. Now, here's the deal. Oftentimes, what we're going to do is, let's actually do this in a different color. We know this matrix should be the inverse of this matrix, which means that it should zero out. So what I'm going to do is I'm going to say that, not zero out, it's going to cancel out. So I'm going to cancel this system out. Now, this is assumed to be correct because we're assuming, which we did, we set up the inverse matrix correctly. If you get a weird answer, or if the answer doesn't make sense, or you're unsure of your process and you want to make sure that you did create the correct inverse matrix, go ahead and actually find the dot product between these two matrices, and you should get that reduced form of 1, 0, 0, 1, which lets you know you did it correctly. We're going to assume that we did that correctly so that we can focus on what's going on over here. Cool. So this is going to give us our x, y. And what we're going to do is find the dot product between these two. So that's going to give us a -2 times -21, or -22, which is going to be a 44, plus a 3 times -18. That's going to give us a -54. The second row, 1 times -22. -1 times -18 is +18, which gives us our xy of -10, -4. Perfect. So that's going to tell us, you can either say, hey, we have our answer right here, or what you could say, or x equals -10 and y equals -4. You could do that as well, depending on the context. Realistically, I would probably go with this, just because it is a matrix system. Should I take that back? Our original question was in an equation format, so I'd probably stick that. So I'd go with the red one. Awesome. So let's look at number 11. Number 11 is one of the first ones when we create our matrix. What do we notice that top equation is all divisible by? This is all divisible by 4. So what I'm going to do is I'm not actually going to use these two systems. I'm going to reduce this. So let me put down, I'm going to divide this top one by 4. So I'm going to deal with a 3x plus y equals, let's see, that's a 16. 10x plus 3y is 48. This is the system I'm going to be using. Okay, so let's take a look. I need to figure out, first off, actually, let's write the determinant over here. So my determinant is going to be AD, so A times D. So I have 3 by 3 minus BC. So 1 times 10. 1 times 10. This is going to be 9 minus 10, -1. That's going to go in the bottom of that. This is another easy scale to plug in, so we're probably going to plug that immediately in. The next thing we're going to do, and we're kind of jumping ahead here, we're assuming that we've created the matrix. I'm going to swap these two values, which you won't be able to tell because 3 is swapped with 3. And I'm going to change these two values. So that's going to be a -1, and that's going to be a -10. Awesome. So now when I create my system, again, I'm assuming by creating this, I've already created my system. So 3, 1, 10, 3. X was the first variable, y was the second. I'm going to leave some space. 16, 48. Awesome. So I'm now going to take this and I'm going to write this from the left-hand side on both sides of my equation, which means because that's an easy fraction to plug in, I'm going to go ahead and stick that into the inverse matrix, which means I'm going to change that to a -3, +1, a +10, and a -3. They all change signs because what I did was I forced that scale into the matrix. You don't need to do that, but again, this was an easy thing to do, so in my opinion, why not? Okay. We're going to assume we set this up correctly, and that's going to cancel out, which is going to leave me with my XY matrix. I'm going to find the dot product of what's going on over here. So I have -3 times 16. That's going to give us, what, 30, 48? -48 plus 48. And then for the second row, 10 times 16 is going to be 160. 3 times 48, well, 3 times 50 is 150. Minus 2, 4, 6. That'd be 144. So -144. If I did my arithmetic right. It's going to be with an x, y. 0. Let's see, that's going to give us a positive 16. I'm going to go ahead and double check to make sure I did that right. Let's see, 10 times 16 is going to give us 160. The -3 times 48 is going to give us a -144. Okay, so yeah, that 160 minus 144 is going to give us a positive 16. There we go. So again, you could put this as your answer. However, because my answer was originally in equation format, I'm going to go ahead and stick with my x is 0 and y is 16. We're going to keep that as our final answer. Awesome. So now that we've seen two of those, why don't you go ahead and try out number 13 on your own? Pause the video, unpause it when you're done, and see how you did. Okay. So now that you've had a shot at that, let's go ahead and take a crack. Okay. This one I know I can divide by 4, so that's going to give me a reduced system to work with. So 2x minus 7y is 12. -2x plus y is -12. So that's my system that I'm going to create. Now you might spot that I can use elimination on this really quickly and get my y, but again, we're practicing using the inverse matrix just to get the process down. I know I could probably solve this in a different way faster. Okay, so that's going to set me up with a matrix that looks like this. So 2, -7, -2, 1. My x was first, my y was second. I'll leave some space. 12, -12. Next thing I need to do is figure out what goes in here, and so I'm going to come do that. Kind of out of order, but the determinant is going to be AD minus BC, so -7, -2. That's a positive 14, so 2 minus 14 is -12. I know that -12 is going to be multiplied into this. I'm going to swap these numbers, so that's a 1 and that's a 2 now. I'm going to change both those signs, so 7 and 2. And I have that 1 over -12. Now this one, I'm not actually going to force that scale in there. I'm going to leave it out. And that way I can deal with whole numbers and then take the 1/12. I can plug it in, I just don't really feel like doing that, so I'm not going to. As long as the matrices are done in the correct order, this times this times this times this, and we keep moving forward, the scale can just hang out whenever we're ready for it. So 1722, 1722, and I have the scale that's hanging out here, so -1/12, -1/12. I know theoretically if I've done this correctly, this should all cancel out, and I'll be left with an XY. And I'm going to scoot this over here and say this is my XY matrix. I'm not yet going to plug in that negative 1/12. I'm going to wait until I've multiplied these two. Okay. So if I find the dot product of the first row, 1 times 12 is 12, minus 7 times 12, that's going to give us 70 and 14, 84. And 12 minus 84 is going to give us, let's see, that's going to be 72, negative 72. For the next one, 2 times 12 is going to be 24. Minus 24 is 0. Negative 1/12. And now, at this point, now that I've done the whole number aspect of this, I'm going to then force in my coefficient. So I'm going to divide that by 12, which is going to give me a 72 divided by 12. That should be a 6. So negative, negative, that's a 6, 0. Could say that's my answer, or realistically what I'm probably going to say in this situation is x equals 6 and y equals 0. And there we go.